right, ladies and gentlemen, we're going to take a look at section 8.3 in today's video, which talks about the concept called polar coordinates. And we want to think about polar coordinates as a new way to plot points on the plane. So, since we want to talk about a new way to do this, let's make sure we understand the old way, what we mean by the old way. The old way is to use what we call rectangular coordinates, also referred to as Cartesian coordinates. Rectangular coordinates may be a better name to actually describe what this looks like. Cartesian coordinates is just an homage to René Descartes, who was the mathematician who popularized this technique. And in this old way, what we view is this. We have our coordinate system, and we wish to plot a point, and the point we're going to plot we call x comma y. And so you go to the x coordinate, then you go up to the y coordinate, and that's the point called xy. And we can refer to this as rectangular coordinates because you can view this as going over x and up y, or up y and over x. Either way, you get to the same point. And by doing both ways, you can sort of envision a rectangle describing the position. Now let's talk about this new way, or polar coordinates. Here we want to plot a point given as r and theta, where r is the distance from the origin to the point, and theta is the angle between the polar axis, as we'll have to describe what that is in a minute, and the point. And the way this works is we have, instead of an xy coordinate system, we can envision this. You've got this line segment right here that we call the polar axis. And relative to this polar axis, we're going to describe an angle, theta, giving the position of the point in terms of a direction. And then the r is the distance out from the origin to the point. So on this, what we would have is, say, a circle like that. That's all the points that are 1 unit away from the origin. Then you may have another circle. That's all the points that are 2 units away. Another circle, illustrating all the points that are 3 units away, and so on and so on and so on. And then you may also have on here these line segments dashing out for various angles being described. This could be the angle that's 30 degrees from the polar axis. This is the angle of 45 degrees from the polar axis. Here's 60 degrees. Here's 90 degrees, and so on and so on. 120 degrees, 135 degrees, 150 degrees. Here's 180 degrees, 210 degrees, 225 degrees, 240 degrees, 270 degrees, 300 degrees, 315 degrees, 330 degrees, and of course this one right here, that would be 0 degrees, or if you went all the way around, it would be 360 degrees. And so what we're envisioning here is what graph paper would look like if you were to plot points in this polar coordinate system. As opposed to up here in the rectangular coordinate system, you know what graph paper looks like up here. Typically looks like this, where you've got a bunch of grid lines forming squares, right? One unit in the x direction, and all these one unit in the y direction. So that's what your graph paper looks like in rectangular coordinate systems, right? These little squares for you to go over and up on. Okay, well, this is what graph paper looks like in polar coordinates. And so if we wanted to plot a point, let's say plot the point, and let me use some different colors here. Suppose I wanted to plot the point, say 2, 60 degrees. Well, what I would do is first go to the angle from the polar axis, an angle of 60 degrees up, and then I'd say, okay, along that angle, let's go out 2 units. So from the origin, 1, 2, there's the point, 2, 60 degrees. Okay. If I wanted to plot the point, say 1, 30 degrees, well, then from the polar axis, I go up 30 degrees, and I go out 1 unit. So that's to the first circle. There's 130 degrees plotted. If I wanted to plot the point, let's grab another pen here. I wish I had more colors. That would certainly be fun. Let's plot the point, say, 3, 180 degrees. Well, then go from the polar axis 180 degrees, then go 1, 2, 3. There's 3, 180 degrees plotted. Okay? All right, let's plot some more here. Let's plot the point -2, 45 degrees. All right, so go to the angle 45 degrees. Here it is. Now, if I was plotting a 2 as the R value, you know, along 45 degrees, I would go 1, 2, and there would be the point. When we have a negative on our R value, when the negative is on the distance from the origin, what that means is find the direction you've told and simply go in the negative, go in the opposite direction. So instead of going 2 along 45 degrees, we're going to go 2 along the opposite of 45 degrees because of the -2. And that's how we plot that. Okay. All right, let's plot the point. Say 225 degrees. So I go to the angle, polar axis 225 degrees. There it is, this angle, and go out 2, 1, 2. There it is. Okay. And of course what you notice is these are the same point. Now that's where the interesting thing about this comes up. When we plot points in rectangular coordinates, if I want to plot the point, say 3, 4, I go 3 in the x, 4 in the y, and there's the point. There is no other way for me to represent that point in rectangular coordinates. Every point has a unique representation in rectangular. Every point has a unique representation. There is only one way to write the point in rectangular coordinates. Quite the opposite is true in polar coordinates, and that's what makes polar coordinates so interesting. Every point not only has 2 ways to write it, every point has an infinite number of ways to be written. So this point can be written an infinite number of ways. An infinite number of ways with a 2, just think about it. You could go around that angle like we did, 225 degrees, or you could go around all the way plus another 225, or you could go around twice plus another 225 degrees, and on and on and on. And you would get an infinite number of ways to write that point. Same thing with the negative. You could go to this angle and go -2, or you could go all the way around once, then this angle, then -2 in distance, and on and on and on. Every point has an infinite number of ways to be written. And that's quite a difference between only one way to an infinite number of ways. Okay. Now let's talk about the idea of converting between these two coordinate systems. Okay. The first thing I'll consider is we want to convert from polar to rectangular. Or you could say polar to Cartesian. That would mean the same thing. Now consider a point given to you in polar coordinates. You've got this polar axis, right? You've got all these angles plotted on your polar graph paper. You get the idea. Circles for distances, right? You've got this point out here. And that's given to you as, say, r theta. And you want to convert that to an x and to a y value. Okay? Well, simply superimpose on here a coordinate system. Throw an x, y coordinate system onto it and say, how would I go about finding that x? And how would I go about finding that y? Well, again, what you're given is the distance r and the angle theta. So think about simple right triangle trigonometry, because you've created a right triangle here. X is the adjacent side of this triangle. X is r cos theta. Y is the adjacent side, or the opposite side of that angle, right? So the y value is r sine theta. And that simply comes from the definition that cosine of theta is x over r, and sine of theta is y over r for any circle that goes through that point, xy. Okay? And there is your formula there for converting from polar coordinates into rectangular coordinates. Okay, so let's look at an example of doing this. Suppose you wanted to convert, say, 3, 60 degrees to rectangular. Well, you would say x is r cos theta. That's 3 times the cosine of 60 degrees. Then do the evaluation. The cosine of 60 degrees is root 3 over 2, so you get 3 root 3 over 2 for your x value. For your y value, you get r sine theta as the conversion formula. 3 times the sine of 60 degrees, once you plug in the r and the theta. You evaluate the sine of 60 degrees, you get, oops, I'm doing those backwards, aren't I? Yeah, this one is a half. So you're getting 3 halves, sorry, and the sine of 60 degrees is the one that's root 3 over 2. So I get 3 root 3 over 2 for the y. So the conversion is this point becomes x is 3 halves and y is 3 root 3 over 2. And there's our conversion. Okay? Try another one. Let's try one from the book, perhaps. Let's try number 10. We want to convert 4, 7 pi over 4 to rectangular, or again Cartesian if you want to call it that. So x is r cos theta. That's 4 times the cosine of 7 pi over 4. When you're doing the y, r sine theta, that's going to be 4 times the sine of 7 pi over 4. Okay? Now, the cosine of 7 pi over 4 is going to be root 2 over 2. And the sine of 7 pi over 4 is going to be negative root 2 over 2. 4 divided by 2 is 2, so you get 2 root 2 here. Here, 4 divided by 2 is 2, you get negative 2 root 2 here. So this point has converted to the point 2 root 2 comma negative 2 root 2. And there you have it. Okay? All right. Now, what about converting in the opposite direction from rectangular to polar? So let's think about that. You've drawn this rectangular coordinate system, and you've got this point. You're given the x, y coordinates of a point, and you want to convert it to polar. So you want to find r, and you want to find theta. Well, r is simply the distance from the origin to the point. So that's simply the Pythagorean theorem at play. The square root of x squared plus y squared, the hypotenuse of that right triangle whose sides are x and y. Okay? Theta, think about this. To find theta, you know the opposite and you know the adjacent side of theta. The tangent of theta is y over x, so theta is the tangent inverse of y over x. And there you have your conversion from rectangular, from xy's to polar r theta. Now, one thing to be careful of here, when we use the inverse tangent, you have to recall that the inverse tangent can only see the right half plane. So what we just gave you here is in fact only a method to convert rectangular points from the right half plane into polar coordinates. This method I just gave you only works for points over here in the right half plane. An easy way to say you're in the right half plane if you're giving x and y is simply to say x is positive. Right? When x is bigger than 0, you're in the right half plane. So this is what you do when x is bigger than 0. Okay? The value of y is really inconsequential in this. It's only the x that affects this, right? Because that's what tells you you're in the right half plane. Now, what if you were in the left half plane? What could you do? Well, suppose you were over here at this point, and you want to find the r, and you want to find the theta. When you hit theta is tangent inverse of y over x, the problem is that inverse tangent doesn't know that it's the x that's negative and the y that's positive. That inverse tangent is going to interpret this as if it's the x that's positive and the y that's negative. In other words, it's going to think you're down here. Where you have the negative of each of those 2 points. Okay? It thinks you're here. So when you hit that theta, it's going to find this angle here. So of course, what's wrong with that is you're off by 180 degrees. And so the correction you can do here is simply add to this angle 180 degrees. Sorry, add 180 degrees will go this way, and it puts you at the correct angle. Okay? The r is still the same. Okay? And there's your conversion when x is less than 0. Now, there's an alternate way you could go about doing this. If you didn't want to mess with the theta, if you want to keep it the inverse tangent and use this as the angle, but you want to get this point up here, you know how you would do that? You would simply take the r to be negative so that you go in the opposite direction. So you could take r to be the negative square root of x squared plus y squared and keep the theta as the inverse tangent of y over x. Either way works fine for doing the conversion. Okay? All right, so let's take a look at a couple of conversions here. Suppose we want to convert the point 3, 4 to polar. So you go over 3, you go up 4, there's the point I want to convert. I need to find the r, I need to find the theta. Well, r again is the square root of x squared plus y squared. So that's the square root of 3 squared plus 4 squared. That's 9 plus 16 under the square root. And I get, of course, r to be 5. Now, what about the theta? Theta is the inverse tangent of y over x, where y is 4 and x is 3. And so let's see where the calculator is. All right, here. Let's go ahead and use that calculator and get the angle. And again, I personally don't much care whether you work in degrees or radians, whatever you feel more comfortable with. Oftentimes the book will work in radians when it gives you these exercises. So just be aware you're going to be looking at a lot of radian angles when you do some of these exercises. Inverse tangent of 4 divided by 3, and we get the angle 53.13, and on and on and on. That's certainly good enough for our purposes. So this point, 3, 4, when I convert it, becomes the point whose radius is 5 and whose angle is 53.13 degrees. If we wanted to work this in radians, I would simply put my calculator into radian mode, and then I'd hit the inverse tangent of 4 over 3, and I'd get my angle in radians, 4.13. And so if you write it without the degree symbol, I understand that means radians. With the degree symbol, I understand that means degrees, of course. Okay, I'm going to put myself back in degree mode before I forget. There we go. I always like to be in degree mode. All right, let's try a second example. Let's convert, say, the point 1, 2 to polar. So x again is the square, r, right, is the square root of x squared plus y squared. That's 1 squared plus 2 squared. 1 plus 4 is 5. Square root of 5 is my radius. Theta is the inverse tangent of y over x. So the inverse tangent of 2, and I get the angle 63.43 degrees. Okay, so the point 1, 2 converts to the radius of root 5 and the angle of 63.43 degrees. Okay, all right, let's try one more, and let's make sure we do one where we're converting from a position to in the left half plane. So how about we take the point, say, -3, 5, so that our x is negative, okay? In other words, -3, 5. This is the point we're trying to convert into polar coordinates. So I want to find the radius, and I want to find the angle to describe that, okay? Well, remember, there are two ways to do this for x less than 0. And certainly -3 is less than 0. One way is you simply use r as the square root of x squared plus y squared, as you did prior. So you get 9 plus 25. That's 34 under the square root. And then when you do theta, you do the inverse tangent of y over x, but then you correct it by adding 180 degrees to it, because again, you're in the left half plane, your x is negative, tells you that. So let's see, 5 over -3 plus 180 degrees. And remember, your inverse tangent doesn't know whether that negative's on the 3 or the 5. It's going to interpret it as if the negative's on the 5. It can only see the right half, right? It thinks you're using the point +3, -5 down here, okay? All right, so let's see what our calculator tells us. Inverse tangent of 5 divided by negative 3 gives us negative 59 degrees, and then I add to that 180 degrees, and I get 121 degrees, basically. I'll round it. So that's an angle of 121 degrees. And so this point, negative 3, 5, becomes the point, square root of 34 is the distance from the origin, and 121 degrees is the angle from the polar axis to the line up to that point. Okay? Or, remember, there was a second way you could think about this. You could let r be the negative of the square root of x squared plus y squared, and let theta just be the tangent inverse of y over x, and not correct the angle, but instead correct the radius, or the distance from the origin. So of course, the only difference there, you'd have a negative, and your theta here, remember what that was 59, negative 59 degrees. Okay? So you could say the point negative 3, 5 is the point negative square root of 34, negative 59 degrees. Okay? Alright, so that's it for converting the points. Now, let's take a look at the idea of converting equations, which is very similar, really not any more difficult. Suppose you want to convert rectangular to polar. Well, all you have to do is in your rectangular equation, meaning your equation with x's and y's, you replace every x you see with r cos theta, and every y you see with r sine theta. And then very often you can simplify. Now, it's not technically, you don't have to simplify, but the textbooks are going to simplify these expressions, so you might as well do a little bit of that simplification, and that way you get used to it. Okay? So let's see a simple conversion here. This is problem number 16 from the exercises, where you're given this very simple equation in rectangular coordinates. This is the line x equals 3. And you know what that line looks like in rectangular coordinates. Here's the xy plane. X equals 3 is right here. It's just a vertical line. Okay? And we want to convert that to polar coordinates. So what I'm supposed to do is wherever I see an x, you replace it with r cos theta. And so the equation written in polar coordinates looks more difficult, doesn't it? It's r cos theta equals 3, which you could then rewrite. You could divide by cos theta, and then you could realize, you know what, the reciprocal of cos theta is sec theta. So that would be a way to write sort of a simplified version of this, which certainly doesn't look simple at all, does it? This line in rectangular coordinates is extremely easy for us to understand. X equals 3, oh, that's a vertical line at 3. When we write it in polar coordinates, it's messy. And so what you start to get an inkling to in just this very first example is, for some equations, like this one, for some equations, the rectangular coordinate system is an easier system to work in. It gives you equations that are simpler than they would be in the polar coordinate system. Okay? All right, let's take a look at another example. Let's take a look at number 18, where the equation is y equals 4x squared. You replace the y with r sine theta. You replace the x with r cos theta. There's your polar coordinate equation version of this. So this parabola, y equals 4x squared, this parabola, that's how you would write it in polar coordinates. Now you can simplify this a little. R sine theta is 4 times r squared cos squared theta. You can divide both sides by r if you want. Then you can divide both sides by 4 cos squared theta. And you solve for r. Now, sine over cosine is a tangent. 1 over cosine is a secant. That would be a way to write this in polar coordinates, and of course it looks quite ugly, doesn't it, compared to in rectangular coordinates where it looks rather simple. All right, one more example to consider here. Number, which one did I want to do? Number 24, yeah. X squared plus y squared equals 9. Now you may recognize that, I hope, it as the equation of a circle centered at the origin whose radius is 3 squared being the 9. When I convert this, again, I'm supposed to replace the x with r cos theta. Replace the y with r sine theta. And there's the version of this equation in polar coordinates, and it may not look simpler yet, but let's see what kind of a simplification we can do. When I square this out, r squared cos squared theta plus r squared sine squared theta is 9. I can factor out the r squared, and cos squared theta plus sine squared theta is the Pythagorean identity. That's equal to 1. So you simply get r squared is 9, and if you take the square root, you get r is 3, or you could get r is negative 3. Either way, you're getting the same equation. When you say r is 3, from your polar axis, that's saying go out 3. But it's not saying any angle, so it's along all angles, and that's the equation of a circle of radius 3. Likewise, go out a distance of negative 3, but go out a distance of negative 3 along every angle, it's the same. Okay? So this is an example of an equation that is simpler in polar coordinates than it is in rectangular coordinates. Okay, that's immediately obvious to us. Oh, if you go out 3, that's just a circle of radius 3. Okay? All right. Let's take a look at now the idea of converting from polar to rectangular. Okay, so we have to convert our r and we have to convert our theta. Okay, so how do we do that? Well, you replace r with the square root of x squared plus y squared. Now, how do we convert our theta? Well, theta, you remember, is the inverse tangent of y over x, right? Think about it this way, though. If you can replace r cos theta with x and r sine theta with y, that will be much simpler. And so let's see how we can make that happen in some of these problems. Let's start with problem number 28. In 28, the equation that we're given is r equals 3 sine theta. Now I know how to handle the r, but over here I don't have a r sine theta, I just have a sine theta. I wish I had an r sine theta, because then I could just put a y there, right? Well, let's make this become r sine theta, and the way we do that is we multiply the equation by the letter r. And of course, since you're multiplying both sides of the equation, you're not really changing the equation. R squared, if r is the square root of x squared plus y squared, then r squared is simply x squared plus y squared. And r sine theta is y. There's your equation in rectangular coordinates. Let's take a look at number 30. In number 30, we're given the equation that r equals 1 over, sorry, it's 4 over in this case, 4 over sine of theta plus 7 cos theta. And so you look at that and say, how am I going to convert that? Well, if you multiply both sides of the equation by this denominator to clear the fraction, what you'll get over here is r times sine theta plus r times 7 cos theta. And on the right, the canceling will just leave you with a 4. And look at that. R sine theta is y, r cos theta is x, and you're in business. You've got the equation in rectangular coordinates. In 32, we have r equals 2 sec theta. And we want to convert. Well, remember that secant is the reciprocal of cosine. And when I look at it this way, I realize, oh, if I just take that equation and multiply by cos theta, I'll clear this denominator, and r cos theta is x. So that's really just the line x equals 2. Very similar to that previous example we did, where we were converting from rectangular to polar, and we saw that the line x equals 3, written in polar, was more complicated. Right? All right, let's try number 34. In number 34, we have r equals the square root of r cos theta plus 2. Now, what I could simply do here is square both sides of the equation. R squared is x squared plus y squared. R cos theta is x. And there you go. 36. R equals 4. Square both sides. Replace r squared with x squared plus y squared. And of course that is the rectangular version of the circle of radius 4, which is what we have written there in polar. And finally, let's take a look at number 38. R equals 1 over 4 cos theta minus 3 sine theta. So of course what I'm going to do here is clear the fraction. Multiply both sides by 4 cos theta minus 3 sine theta. So r times 4 cos theta, r times a minus 3 sine theta. And on the right, the denominator cancels with that, leaving a 1. And then you say r cos theta, that's an x, r sine theta, that's y. And there's your equation in rectangular coordinates, and it's easy to see, oh, that's just the equation of a line. All right, so this is what lines look like in polar coordinates. This is what they look like in rectangular coordinates. Obviously, rectangular coordinates is a more natural coordinate system for lines than is polar coordinates. Whereas up here, here's the equation of a circle in rectangular coordinates. Here's the equation of the same circle in polar coordinates. Obviously, circles are more naturally graphed in polar coordinates than they are in rectangular coordinates. Okay? All right, so that concludes this section 8.3. Please knock out those homework problems. You should find them pretty straightforward in this section. And then we will go on from there.